How do you know, Captain? I just was told in here. It was just to be here.
I got a feeling
It's too cold to rest.
that tonight's gonna be a good night. That tonight's gonna be a good night. That tonight's gonna be a good night. Feeling that tonight's gonna be a good night. That tonight's
Hi! Cut! 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 What's up, Yoshi? Yoshi! Yoshi!
Plum Brook, a field station of the Lewis Research Center, is located about 50 miles west of Lewis on 6,400 acres of land. This vast acreage provides the required clear zones needed for safely conducting potentially dangerous aerospace tests. Several large, unique aerospace test facilities are located at Plum Brook. These facilities are available to support major national aerospace test programs. One of these facilities, the Space Power Facility, is the world's largest space environment simulation chamber, 100 feet in diameter by 122 feet high. In this chamber, large space-bound hardware can be ground tested in a severe environment similar to that encountered in space. The chamber air can be removed to simulate the vacuum conditions of space up to an altitude of about 145 statute miles. Charged argon gas can be added to the chamber while it's at vacuum to simulate the actual space plasma environment of low Earth orbit. The very cold temperatures of space can be duplicated by means of a cryogenic cold wall, the very hot temperatures by means of a quartz lamp heater. Even the actual sunlight experienced in space can be simulated with an existing 400 kilowatt arc lamp. In 1989, under a cooperative agreement between the General Dynamics Corporation and NASA, this chamber supported payload fairing separation tests for a new generation of Atlas I launch vehicles. A few months after testing at Plum Brook, the newly designed fairing successfully protected the combined release and radiation effect satellite as it was launched into low Earth orbit on board the Atlas Centaur vehicle. In 1990, the Space Power Facility qualified expensive flight hardware for the SDI program. Here you see a 100 kilowatt power supply being processed in a Class 10,000 clean room located inside the huge vacuum chamber. Ground testing of this power supply simulated performance in a high-altitude space plasma environment. More recently, this chamber supported jettison testing of the 86-foot-tall, 16-foot diameter Titan IV payload fairing under a cooperative agreement between the U.S. Air Force, the Martin Marietta Company, and NASA. This fairing, the largest ever tested in a vacuum chamber, had internal payload space dimensions approximating the Space Shuttle Orbiter Bay. Here you see the 10,000-pound Titan IV fairing being jettisoned under vacuum conditions in the test chamber at Plum Brook. Scheduled for 1993 is the Ariane 5 payload fairing separation test for the European Space Agency, and for 1994 and 95, the Space Station Freedom Electric Power Generation System test for the NASA Lewis Research Center, and the Space Station Freedom Laboratory Module Radiator Test for the Johnson Space Center. Not only is the Space Power Facility the world's largest space environment testing chamber, it is also the world's only large vacuum chamber capable of handling the highly radioactive tests that would be needed to develop space nuclear electric power generation systems. This is possible because the chamber walls are made of aluminum, which has a low neutron capture cross-section. This keeps the chamber walls from becoming highly radioactive if a space nuclear power reactor is operated inside. The aluminum chamber is contained within a second vacuum chamber that has 8-foot thick concrete walls which serve as a radiation shield. Adjacent to the chamber is a large disassembly area which also has 8-foot thick concrete walls. This building can be used for remote control disassembly of large radioactive hardware after tests are complete. Although the Space Power Facility has not yet been used for nuclear testing, it stands ready to support such space power supply development programs. Another of Plumbrook's world-class facilities is the Spacecraft Propulsion Research Facility. Here, large upper-stage rocket vehicles can be hot-fired in a simulated space environment. A 38-foot diameter by 55-foot high stainless steel vacuum chamber is capable of simulating pressures of 1 × 10⁻⁶ torr, or about 115 statute miles altitude. A full-sized launch vehicle up to 100,000-pound thrust capability can be loaded in the chamber through the top hatch and secured to the bed plate. A cryogenic cold wall simulates the cold temperatures of space. A quartz lamp heater array simulates the heat from the sun. The facility was designed and built to safely handle the large quantities of liquid hydrogen and oxygen carried on a fully fueled Centaur vehicle. In test firings of fueled vehicles conducted by remote control from a blockhouse a half-mile away, vehicles experience an environment similar to that in space. At the moment of firing, an 11-foot diameter high vacuum valve springs open at the bottom of this diffuser tube and releases the rocket exhaust products to the spray chamber below. The 150-foot deep spray chamber is filled with a chilled water spray that is used to cool down the exhaust from the rocket. At the same time, huge steam ejectors pump out the exhaust products from the firing and maintain a high altitude condition throughout the tests. In 1987, the vacuum chamber portion of this facility supported testing of flight hardware for the SDI program. Ground testing of high-voltage power supplies in a simulated space plasma environment determined flight performance in advance. This facility may be fully reactivated to support advanced upper-stage launch vehicle development for programs such as the Space Exploration Initiative to Mars. The third space environment chamber at Plumbrook, the 25-foot diameter cryogenic propellant tank facility, is being used to develop the technology for storing and transferring liquid hydrogen in space. Recently, an 800-gallon slush hydrogen batch production plant, the nation's first, was constructed at the site to support development testing for the National Aerospace Plane. Here you see liquid hydrogen being converted to slush using the freeze-thaw method in the generator at Plumbrook. Previously, slush hydrogen had been produced only in liter-sized quantities in the laboratory. In addition to its 3 large space environment chambers, Plumbrook also has a large hypersonic wind tunnel capable of performing flow tests at Mach 5, 6, or 7. High-pressure nitrogen gas stored in a high-volume tank adjacent to the facility is released and flows through a 3-megawatt electrical heater that raises its temperatures to nearly 2,500 Kelvin. Then sufficient oxygen is added to the hot nitrogen to produce an air composition. The heated air flows through a hypersonic flow nozzle and past the model. A large steam ejector also pulls a vacuum on the test chamber to help establish the flow pattern and to simulate a high altitude condition. The hypersonic tunnel facility was last used in 1974 to test a hypersonic research engine at Mach 7 conditions under a joint program between the Garrett Corporation and NASA. Currently, it's being reactivated by NASA to support generic hypersonic research and is expected to be operational by mid-1993. The four major facilities at Plumbrook, together with the surrounding clear zone land, the infrastructure, and the trained staff, provide a significant national test capability available to NASA, other government agencies, and the private sector.